Hello guys, welcome to Physics Grad. In this video we are going to prove the Green's theorem. So let us begin. So before you watch this video, I recommend that you watch the previous lectures, which is Maths playlist lecture 10 to Maths playlist lecture 12. Okay, it will help. So let us begin. So let's start by stating what the theorem says. So theorem. So what this says is the following. Let D be a domain of the xy plane, and let C be a piecewise smooth curve. Piecewise smooth, in fact simple closed curve. We already saw what simple closed curve means in one of the previous lectures. Okay, simple closed curve in D whose interior is also in D, whose interior is also in D, which means that the area enclosed by this curve is also inside the domain D. Okay, and let Pxy and Qxy be functions defined and continuous and having continuous first derivatives in D, in fact first partial derivatives in the domain D. Then what the theorem says is that the line integral over the curve taken along the positive direction of the function p dx plus q dy will be equal to the double integral with respect to the region R enclosed by the curve times dou q by dou x minus dou p by dou y dx dy. Okay, so let me call this equation 1. So this is what the theorem says. The relationship between the line integral over the entire curve taken in the positive direction is going to be equal to the integration over the region enclosed by the curve of the function dou q by dou x minus dou p by dou y. Okay, so here R is the closed region bounded by the curve C. Okay, so what we will do is first we are going to prove this theorem for a special case when R can be expressed in the following manner. Okay, so first we will prove one for the case in which the region R is representable in both of the forms given by a less than or equal to x less than or equal to b, f1 of x less than or equal to y less than or equal to f2 of x. I'm going to show you what this means soon. C less than or equal to y less than or equal to d, g1 of y less than or equal to x less than or equal to g2 of y. So what this means is the following. If you have a curve which looks something like this, a simple closed curve, this is x which is looking something like this. Okay, then I am going to define this as point A, this as point B. Then this function, that is the function which represents this particular curve, is going to be f1 of x, and this particular function is going to be f2 of x, and our y at every point in x, for example here if you consider, will begin at f1 of x, that is what this means, and it goes up till f2 of x. Okay, this is one way of representing the region. Okay, so this region has all possible values of y ranging in this region for every value of x. So that is what this inequality means. Similarly, I can consider the point like this, this as C and this as D, and now I can define these curves from here like this up till here as g1 of x, g1 of y, and this curve as g2 of y. Then if I take any particular value of y here, then this region will include all the points wherein x will start from g1 of y and end at g2 of y, and that is what this particular inequality says. Alright, so now consider the double integral in the region R of the quantity dou p by dou y dx dy. Okay, now this in the form of double integration can be written, if we consider this particular form, this can be written as integral from a to b, integral from f1 of x to f2 of x of dou p by dou y. First I integrate it with respect to y, then I integrate it with respect to x. So if I do this, what I'm going to get is a to b. So integrating this guy with respect to y is going to give us p, and substituting the limits we get p of x comma f2 of x minus p of x comma x1 of f1 of x dx. Okay, but this can be written as integral minus b to a, just changing the order of integration, p of x f2 of x minus integral a to b p of x f1 of x dx. Okay, but if you observe, this quantity is nothing but integrating the function p over the values ranging from point B. So here we are going from B to A. So from B to A, so that corresponds to going from our point B is over here. So we go from here to this point in this manner along this curve. Okay, that is the first part. And similarly, the second part is minus of a to b of the same function with respect to x. So we go in this fashion. So what this means is that we have basically evaluated integral c, in fact minus p of xy dx. Okay, that is what this guy is going to give us. Okay, because that's what these limits tell us. Okay, so we are going from b to a like this, and then a to b like this, which means we have traversed the entire curve, and there is a negative sign as well. So this will be equal to minus integration over the curve in the positive direction of the quantity px f of x is nothing but our y, so I can replace it. So if I combine these two, I can replace our f of x as simply y dx. Okay, because as we go in this range, we are basically covering all of these y values. So that is why it justifies to write or replace f2 of x and f1 of x with y. Okay, and we are going along this curve. So let me call this as equation number 2. Okay, what is this equal to? This was equal to our LHS was this guy. So this was equal to integral r dou p by dou y dy dx. Okay. Similarly, I can calculate integral r dou q by dou x dx dy. And if you follow the same steps, what you will see is that this will be equal to positive of the integral over the curve times q of xy dy. Okay, so this can be obtained in a similar fashion as how we obtained this. I leave it as an exercise to you. Now if we do the following operation, that is 3 minus 2, what we get is that integral over the region r dou q by dou x minus dou p by dou y dx dy will be equal to integral over c p dx plus q dy, which is nothing but our equation 1 which we have here. So therefore we have proved the Green's theorem for the case when our region can be expressed in this form. Okay. Now what if we cannot directly express the region in that form? Then how do we prove it? So suppose R is not itself in this form but can be decomposed into finite number of such regions. Okay, so let's call these regions, decomposed regions, as R1, R2 dot 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 Rn. And how do we do this? We can do this by suitable lines or arcs. I'm going to show this using an illustration. Okay, so if you consider in our xy plane and we have some complicated region which may look something like this, say, okay, then this may not be, we may not be able to express this region in a form, simple form like this. So what we will do is we will divide this into parts wherein we can, so I call this R1 or R1, R2, R3. Okay, then our region R is nothing but R1 plus R2 plus R3. Okay, and what we can do is if we want to calculate the integral around this particular curve C, this will be nothing but integrating along this curve first, okay, like this, and then integrating along this curve like this. So this I'll call C1 and this I call C2. Similarly, if I integrate along this curve like this, this will be C3. Okay, so here you notice that when we integrate along C1, C2, C3 and add them up, it will simply be equivalent to integrating along the curve C, because in each of these regions, once we integrate in this direction and once we integrate in this direction, so that will cancel each other. So it will become clear when we write down the equations. So now what we do is that we have broken down the entire region into individual regions, which are individually will be able to we will be able to represent them in the form as we had seen before, that is in form of simple inequalities. So if we do that, we can apply our result 1 to each region separately and add them. Okay, So basically what we'll do is, for the first region, if you consider, this will be integration over C1 p dx plus q dy, and for the second region, integration over C2, again p dx plus q dy, and so on to the nth region, Cn, p dx plus q dy, and corresponding values will be R1, double integration over R1, dou q by dou x minus dou p by dou y dx dy. So this is when we apply the first equation 1 to just this part. Okay. Similarly, we have n terms here. Rn dou q by dou x minus dou p by dou y dx dy. Now our LHS is going to be simply equal to integral over the entire curve C times p dx plus q dy, since integrals along the added arcs, in this case the added arcs corresponds to these two lines. Okay, so the integration along them are taken once in each direction. So what we are doing is that we are integrating in this direction once, that is in this direction once across the same function p dx plus q dy, and then again integrating in the opposite direction once with respect to the same integrand, which means they will cancel each other, and what remains is just these parts. So totally what remains is just the entire curve C. Okay, that is what this statement means, direction, and hence cancel each other. Okay, so this implies the remaining integrals will add up to integral over the entire curve C p dx plus q dy, and that is why we can write LHS as this. Okay, and the RHS is just the sum of the same quantity, or sum of the integral of the same quantity over the regions R1, R2, R3 and so on, and if we add them up we get the double integration of the quantity over the entire region. Okay, so our RHS is going to be simply integral over the entire region dou q by dou x minus dou p by dou y dx dy. So therefore, comparing these two, this is again in the form 1, which now we have proved for a random R, which is usually the practically possible types of regions R. Okay, now you can also express some weird mathematical region which may not be practical, and that will require more rigorous derivation, but for practical purposes this will suffice, and therefore we have proved one is proved for all practical curves or regions. Okay, so that's all I wanted to do in this video. We have basically proved the Green's theorem for regions of this kind, which can be expressed if broken down in terms of inequalities. So thank you for watching. See you next time.